All right, welcome. Section 2.3, what we're talking about here is real zeros of polynomials. So what we're going to be working with a lot here is division. We're going to talk about two different types of division, long division and synthetic division. So we'll start with long division. So division of polynomials. Recall long division with numbers. So if we were talking about how do we divide 136 by 20, well, we'd write 20 and 136. Then the process that you follow is you say, how many times does 20 go into 1, which is 0? How many times does 20 go into 13, which is 0? How many times does 20 go into 136, which is 6? Or you could be saying, what times 20 is going to give me the largest number down here that I can subtract from and still get a positive? So 6 times 20 gives me 120. And I subtract going down, so I get 16. Now, looking at this, there's some vocab here that we want to keep in mind. So right here, what we have is our quotient. The 20 is going to be our divisor. It's the thing that we are dividing by. The 136, the thing that we are actually dividing, is called our dividend. And the 16 is our remainder. We're going to use this same sort of algorithm of like what times 20 can go into 136 and get some remainder to divide out polynomials. So if we do an example with polynomials, we're going to use that algorithm to divide. So if I have x squared minus 4x minus 12 and I'm dividing by x minus 6, I'll write out that same thing. So here's my dividend, x squared minus 4x minus 12, and I'm dividing by x minus 6. So I say, okay, what times x, I'm not really concerned with the minus 6, I deal with that, but in a different way. What times x gives me x squared? That would be x. This x gets multiplied to both of these. So this is going to be x squared minus 6x. What I'm doing now is subtracting downward. So x squared minus x squared cancels. Negative 4 minus negative 6. And for some people, that's a little bit tricky. So it's totally okay if what you do right away is just switch these signs, in which case we're going to be adding. So notice I just sort of distributed that negative down here because I'm subtracting this whole thing. That gives me 2x minus 12. Now I say again, what times x will give me 2x? That would be a positive 2. So when I multiply, I do 2 times x, which gives me 2x, and 2 times negative 6, which gives me negative 12. Again, I'm subtracting, but if I wanted to add, I just change these signs. Here this cancels, here this cancels, so I get 0. Using some of that vocab then, our remainder is 0. Our divisor is x minus 6. That's the thing that I'm dividing by, that whole binomial. My quotient, the thing that I was left over with, which I spelled wrong there, quotient, there we go, is x plus 2. That's what I got after performing the division. Just going back a slide, something that would be helpful for us to keep in mind is that if we talk about the dividend, this thing that we had inside here, the dividend is equal to what you get if you do the divisor times the quotient. So if I do 6 times 20 and then add in the remainder, I get the dividend. So here, x squared minus 4x minus 12 is what you get if you do the divisor, x minus 6, times the quotient, x plus 2 plus the remainder, plus 0. If you wanted, plus 0. So if I were to multiply this back out, I'd get x squared minus 4x minus 12. Our answer here, however, when we divide, it's just this x plus 2. That would be our answer because there's no remainder. All right, so the division algorithm. Division is really just a process. It's an algorithm that we're doing over and over. If f of x and d of x are polynomials such that d of x is not equal to 0, and the degree of d of x is less than or equal to the degree of f of x, there exists unique polynomials q of x and r of x such that f of x is equal to d of x times q of x plus r of x. So the division algorithm, we're talking about doing f of x divided by d of x. And what we're really just saying here, taking out some of this x notation, is if I have a function and I divide it by a function such that that function is not equal to 0, then the degree of the divisor, the degree of the denominator, has to either be less than f of x or equal to f of x. And as long as that's the case, f of x can be written as the divisor times the quotient plus the remainder. Where the remainder, r of x, is either equal to 0 or the degree of r of x is less than the degree of d of x. So and that sort of is just saying, like, if I have a remainder, that means I can't divide this out any further. If, and this is the case that we're going to be particularly looking for, if r of x is equal to 0, then d of x divides evenly okay, that's not a letter, evenly into f of x. And what you sort of want to be thinking is, like, if I'm dividing evenly into it, r of x isn't there anymore, so I just sort of factored this. It's going to be a different way of factoring. So we'll see some examples of that, like here we'll do an example of it, but we'll do that in the examples video. So then long division is sort of a tedious process. You've got all those x's, they can sometimes be confusing. So instead, we also have synthetic division and synthetic substitution, which is the same idea but with a different purpose. What this is a shorthand version of long division that uses only the coefficients of a polynomial to divide. So if you're a junior or a senior sitting and watching this video, synthetic division is something you've done. If you're a sophomore, you may not remember synthetic division. You may not have done synthetic division. So you sort of got to look through this process. Synthetic division, if I have ax cubed plus bx squared plus cx plus d, where a, b, c, and d just represent coefficients, and it's being divided by x minus k, we use the following pattern. So we list our coefficients. We bring down that first coefficient. And then the process that we follow is we do k times a and bring that up here. And here vertically, you can see you're going to add. So then I would add straight down. Whatever I get here, I would multiply by k and bring up. I'd add straight down, multiply by k, bring up. Add straight down, get a remainder. And you'll see examples of that. I strongly recommend that you go and watch some of those examples because I'm not going to do any of them here. I'm going to, leave it to you. So synthetic division, just a little bit more about it, it can also be sort of called synthetic substitution. And synthetic substitution, it's more just a different goal is what we're looking for in synthetic substitution. Same sort of idea. So according to the remainder theorem, there we go. if a polynomial f of x is divided by x minus k, x minus k, the remainder is r equals f of x. So if a polynomial f of x is divided by x minus k, the remainder is r equals f of x. The factor theorem says a polynomial f of x has a factor x minus k if and only if f of k is equal to 0. So, factor theorem, a polynomial, some polynomial f of x, has a factor x minus k if f of k is equal to 0. So, substituting in that value into the function, that k value into the function, if I get 0, then x minus k is a factor. If a polynomial f of x is divided by x minus k, the remainder is, oh sorry, this is a slight mistake. Just go change that letter, is f of k. So again, what this is saying is the remainder in division is the same as what you would get if you substituted in the k value, which is what you're sort of dividing by. So you'll see more examples that maybe clarify that if you go and just watch a little bit of that examples video. Remember, you can skip ahead in that if you want to. Sometimes you hear some nice stuff though. So then the way that this is going to be used is by doing what's called the rational zeros test. The rational zeros test is all rational zeros, or tells us all rational zeros, okay, will be in the form of plus or minus p over q. So one important thing about this, it's called the rational zero test. I'm just going to make a little note over here. It does not find irrational. Wow, that's an amazing. Let's just irrational. I'm sorry that my spelling is so bad today, or my handwriting, it's extra bad. Or complex roots or zeros. So the rational zero test, what this is going to be used for is finding x-intercepts. And it's a way of testing like what things should I think about trying to divide by, or what things might be zeros. Where p is a factor of the constant, and q is a factor of the leading term. So just to give a little example of part of the rational zeros test, what are all the possible rational zeros of f? So I have this whole thing, and this is saying like I'm not actually giving you a division problem, but I'm asking you what are the things that we would contemplate dividing out? Like what are the even possible things that we should deal with? So what we do is we take 6 and 5. So 6 is where I'm going to get my p from. 5 is where I get my q from. The possible rational zeros is when you do all the factors of p over all the factors of q. So it's plus or minus. The factors of p would be 1, 2, 3, and 6, because I'm doing the factors of 6, over the factors of q would be 1 and 5. So if we wanted to list all of them out, we would say it's plus or minus 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 6 over 1 is 6. 1 over 5 is 1/5, 2 over 5 is 2/5, 3 over 5 is 3/5, and 6 over 5 is 6/5. So if we were talking about performing some synthetic division, again with the goal of getting a remainder of 0, we would have 1, 2, 3, 4, 5, 6, 7, 8, but the positive and negative. So we have like 16 things that we might be doing that division for. So that's a little bit confusing, but if you watch that examples video, you'll see it's actually really, really easy to do. And it's synthetic division. Like some of these problems, you might have to synthetically divide 10 times in one single problem. And you might be doing it right, but just based off which of these numbers you end up picking, you might have to do it more. So you want to get down that process and you want to be able to do it really quick. So go watch that examples video. It's going to be a huge benefit to you.